Okay, with all the tools to compute for limits, we have quite a few of them. So I guess you have yesterday seen and used a couple for computing limits. Okay, so let me just remind you what are the techniques for computing limits. Okay. First of all, the easiest thing would be if you can plug in numbers. That's what I call easy case. Okay. And for example, if you deal with polynomial, rational function, trig functions, in which you can find the value. Okay, so that's limit. And then you have also factorizations and cancellations. Okay, factor you can cancel, okay. And then this is especially works for rational functions. And you can also do some multiplying by conjugate. In this case, you deal with the function with roots. So actually you try to get rid of the roots by multiplying by conjugate. All right, so what else? And here we have, for example, if you x equals a. This is to deal with these functions, rounding functions. Ceiling and roof, ceiling and floor functions. Okay, or you may need to work with the one-sided limit. If you deal with absolute value, for example. Okay. And thing that we learned yesterday is what we call the squeeze theorem. Okay, when you squeeze, you don't work with the function directly, but with the lower bound and upper bound, which has the same limit. Okay, so the idea is how to find the upper and lower bound and compute limit. Okay. And then you have also some special trig function, trig limits. Okay, that is how you call it, the sine x over sine x, tan over x, x over tan, and 1 minus cosine over x. Okay, so that's more special limits. And do the others by somehow multiplying, adding, or something, so that you can find this stuff. what is the next? All right. And the thing here is that by no chance by any chance you cannot use L'Hopital. See, uh, if you recall what you learned in calculus in your high school, there's something that called L'Hopital rule. But we'll see later. Okay. All right. So let's that is the what we learn from limits. All right, and then there are three cases when a limit does not exist. Exists. Okay, and one is this kind of picture. So in this case, limit x equals to 0 from the right is not the same as one from left. So this is the case when the are not equal. What's it? Don't match. Okay. And then the thing is what we call the, you remember this one? Yeah. So that is the case of sine over x. Okay, so this is what we call the extreme oscillations. And the third one, I haven't mentioned it on this, is what we call infinite limit. Something that gets larger and larger. Okay, so this is the case of, for example, here. Okay. X goes to 0 from the right, for example. Something that gets larger and larger to positive direction. Okay, so infinite limit also we say that it is limit does not exist. So three cases. Okay. All right. So now we try to deal with this number 3. Okay. So this is what we call limit, infinite limit. So let's see. Sorry. Should say this is 105. Okay. Limit at infinity. Okay, so let me tell you the role of a limit. Limit for in mathematics is just like a microscope in biology or or in physics, right? Act as a microscope. Okay, try to zoom out behavior near a certain point. Okay, so then example here is that this one, sin x over x. So we cannot see the this behavior, or let's see, no, this one, just this one. X square sine 1 over x, limit x go to 0. All right, so now we know this is extreme oscillations. Okay, and this one's getting to 0. But you cannot just multiply them directly, okay, because one exists limit, but the other one doesn't have a limit. Okay, so you can just use the properties of limit, the multiplication property. So somehow you have to magnify the behavior close to 0. Okay, magnify that x squared sine 1 over x near x equals 0. Okay, so if you try to plot them, what you see is something that looks like this. All right, so this is a, if you think, all right, so this is the oscillation thing. And this is what you call the amplitude, right? Okay, so we draw up the amplitude. Okay, so where's the oscillations? Here's the oscillations. See, the amplitudes just get smaller and smaller. Okay, so we, by computing limit, we try to magnify this one. Okay, and by keep on magnifying, you see this, the limit is 0. Okay, so limit is a kind of microscope. All right. So this thing, let me write down. Limit is microscope. Now, on the other hand, you can, in astronomy, use the telescope to observe faraway objects, stars, galaxies, whatever, right? All right, so let's, you would like to see this kind of behavior. Other direction, I would say. Okay, so you have a function. Okay, so the question is that what happened, and this is the graph. Questions. What happened to graph of f if x is large? Or we can say going far to the right. So this kind of behavior you find from here. You see the limit, but as x goes to There. And so this is looking for the behavior f as x going far to the left. And you can make these things also. So how you read this one? So this behavior f, what direction? In which directions? This minus infinity. What's the directions of this one? This has to do with there. And what about this one? Well, what does this minus sign signify?
Going far to the left, sir.
Going far to the left. So we have the right directions. Okay. So in this case, you see that a limit is equals to telescope. Okay. So that's basically the function of the limit, to see things that's really small or something that's really big, really far away. All right. So this is what we call the limits at infinity. At infinity. Okay. So let's do this one. Okay, I guess you get familiar with this one. Let's see. What about find the following limit? It's going to okay, how about this one? Okay, all right, so going far to the right. All right, so as is going far to the right, so what we should do here, this is rational function, and on the numerator you have a square, but in denominator you have a cube. So what we do, let's remember the tricks. Right, so let's do this one. X squared. Okay, so if you recall the trick of, let's see, what's the highest order from this these rational functions? You have square, you have cube. So this is the largest one. Okay, so what I'm going to do is I divides everything by x cubed. Okay, so divide by x cubed, also divide by x cubed. Okay, so this notations here, what I mean is that you get 1 over x, you see? 1 over x cubed. And you have 1 over x plus 7 for x cubed. Okay, so take the limit. But now we can use the properties of limits, okay? Because each of this one has a limit properties. See, I mean the limit exists. Limit does exist. So what we can do is, it's like computing limit of each one. This is 1. So this is limit x minus infinity plus limit 7 x cubed. All right. And each of these has limit, which is there 0, that's 0, 1, this is 0, and that is 0 also. So in the end, you have limit. Okay. So what it means that far away to the right, it looks like 0. Okay. What does it mean? The limit is 0. All right. So far away to the right, or for x large, far to the right, you see that the numerator is much smaller than the denominator. Although it is true that x squared plus 1 is large, x cubed minus x squared plus 7 is large, but then the denominator is much larger than this one. Okay, because this 0. Square plus 1, plus 1, right? X cubed minus x squared plus 7. Meaning when x gets larger, okay, so that's correct. Gets larger. X squared plus 1, x cubed minus x squared plus 7 also gets larger. Yeah. However, x squared plus 1 is much smaller than x cubed minus x squared plus 7. Why? Because this is small. And you see that the difference here, the 0 here is meaning limit. So this means something small. Small. Okay, so it's not really 0 in terms of numbers, but in terms of limit, 0. Meaning as numbers, it's really small numbers. Okay, so that's one of the trick, you know, that the just divide by the largest term. In this case, largest term would be x cubed. Okay, so this trick. Divide by the largest term. In this case, term with highest power. Okay. All right, so what about
Sir, I have a question.
sure.
For the second part, the one before 0 plus 0 over, is that limit x near 0 or near infinity? I can't tell.
Near infinity, going to infinity.
Oh, then how'd you get 1 over infinity equals 0? How is that?
Oh, I should, this one. Oh, this one. All right. Yeah, I forgot. I haven't explained that one. We'll do that one. Okay, so let's see. All right. So in that case, I should mention this one. So that's assuming This limit, you know this limit. X, limit X going, and so forth. Okay. Or better yet, oops, sorry. Has the screen back to OneNote?
Yes, sir.
Okay, good. Let's see. In fact, you have 1 over x to the k is always 0. Okay, so how do we know this one? So we need this one first. Okay, let's do this one. Okay. Recall the epsilon delta definition of the functions. Okay, so limit x minus s going to the far to the right of f of x equal something, meaning that f of x or we gets close to L as x gets larger. Okay, so do we have to give a meaning to what does mean for gets closer and closer to L? That means close or far is about distance. There. Okay. Gets closer and closer is that this is some less than something here. Okay. Gets larger and larger. What's gets larger and larger? Large. That means x going to be larger than some number m. Okay, so in other words, you can make this error as small as possible by making x as large as finding the m. Okay, make the error as small as you like by making x large. The thing is, question is how large? M large. Okay, so in the end, you have these definitions here. For every epsilon positive, you can find this m, the measure of largeness. So that x minus L smaller than if you take x larger than this m. Okay. So what about this one? Okay, so let's apply this to show this this limit. 1 over x is small. Okay, so let's do some scratch thing. Okay, so 1 over x is, let's just write this down first. Okay, so this f of x minus L. All right, so this just absolute value. We want to have there. We need this one. Okay, so what we need here, 1 over x. So because this is a non-negative number should multiply by absolute value of x. So then you have this. Sorry. And oh, just the other way on. Okay, so this tells you that how large is you take reciprocate reciprocate. Okay, let's see. Okay, yeah. So just 1 over. This refers the the inequalities. So that's basically your M. So this is the choice for M. Meaning that the proof should looks like this one. That epsilon be positive. We choose M equals 1 over epsilon. Right? So for x, which is larger than M, which is 1 over epsilon, so we compute this one. Okay, so which is, well, if you replace x by something smaller, you get this inequalities. M, which is 1 over epsilon, which is epsilon. Okay, so that's the proof of is 0. Okay, so how's the proof of this one? Okay, so that's easy because this is 1 over x squared. This is limit 1 over x times this limit, because each of the limit exists. Okay, so that's 0. In fact, this limit of 1 over x to the k, you can say this is 1 over x k. When this is 0, there we go. Okay, from what? 1, 2, 3, 4. Okay, so can use this fact to complete this one. Okay, so that's for rational functions. For rational function, as long as the numerators is smaller power than the denominator, then it goes to 0. Okay. On the other hand, what about they are of the same power, up and down? Back to example. Let x goes to part the right. So there. So in this case, everything would be divided by x cubed. Why? Because the largest term would be x cubed, right? So the largest term x cubed. So when we divide by x cubed, so you get 2, 7 over x, 7 over x, 7 over x cubed. And then the denominator, you have 3 5 over x squared minus 10 over x x cubed. All right, so this one goes to 0, small. This one is small because 7 divided by something large, small, small. So in the end, you only left with this one. Okay, just 2/3 is the answer. Okay, so how you read this one? So numerator is gets larger as x goes to far to the right. Okay, so x, when x large, the numerator is large, denominator is also large. Okay, so but in this case, you see that the ratio is a number. So that means, well, the numerator is roughly 2/3 of the denominator when x is large. Okay. So in this case, large divided by large is you get a number. In this case, sorry, let me move to this one. You see this one is large over large, but you get 0, meaning that the numerator is smaller, much smaller. Okay. So that's, well, that's one reason we call this large over large thing is called the indefinite, because this can give you anything, can give you 0, can give you a number, or may give you also infinity, means getting large. So it can be small, can be large, can be anything you like. Okay. All right, so this give color. Let's do this one. See? You may guess from beginning, well, this is what we learned yesterday, so this one should be 1. But no, that's 1 is the ratio when x is small. Recall a minute. When x is small, this is 1. But this is the case. Oh, sorry. Yeah, small. But this is the case when x is large. Okay. But the thing here is that sine x is only the value of sine x will fall between -1 and 1 while x gets larger. So you keep dividing something that we finite between -1 and 1 with something large. So you end up with something gets smaller and smaller. It then should be 0. Right? So this is sine x is bounded. When x gets larger. So what we have is finite over large. Okay, so it should be small. But how to justify? All right, so let's do this trick again. So you see that sine x value is negative between -1 and 1. Okay, and then multiply by 1 over x. X on 0, of course. Okay, but this is automatically satisfied because we're going to infinity. We're going far to the left. So we'll be far away from 0. Of course, not 0. So this would be smaller than x, be smaller than 1 over. Okay. But the limit 1 over x is the same as, sorry, 1 over, so this is equal to 0. Okay, so by squeeze theorem, this limit 0. Okay, so I use squeeze theorem in this case. Okay, so that's the, let's do this one also. That is number 5. Find this limit going far to the right of, well, this is the floor function divided by x. Okay, so divided by x, this is okay because this x getting large. So the danger is when x small, going to 0, but when the x is large, then no problem with this one. Okay, so how we compute this one? Okay, so observe that you have a real number. Okay, so x real number. But a real number should be between 2 integers. N plus 1. Okay, so we can find n plus 1. So what do I call this? Find integer n such that x, right? So any real numbers is between 2 integers. Okay, so this may equal, so that's why. So in this case, when you compute let's see, when you compute this floor, you get, what's the floor of this x? What is the floor of x in this case? What is the floor of x? How would you compute floor of x? If you round x, what? Just n, right? Just from this number, from this picture here. Okay. And again, looking at this, how do you position x minus 1 and x plus 1? How do you put x plus 1 and x minus 1? Well, is x minus 1 here or here? Cannot be here, right? Because you subtract 1 from x. So it should be to the left of x. But where you should put it? Between n and x, or to the left of n? So this is distance 1. So where you should position x minus 1. So you subtract there, right? So this is x minus 1. And well, where should you put x minus, sorry, x plus 1? Same thing. So here we have. So from this, what we have is x minus 1. Right? So let's n. This is x. This is n plus 1. This is x plus 1. Okay. So because from the left to the right, distance 2. Here's distance 1. Okay. So let's see this one here. No, because let's do the squeeze thing. All right, so when you have absolute value of x, okay, and this is equals n, right? So this n is between x minus 1 and x plus 1. Okay. So assume x is positive. Why you should assume x positive? Well, so that when you divide this by x, it doesn't change the sign. Sorry. Okay. All right, so then this is positive. All right, so what you have is x minus 1 over x. Is x plus 1 over x. Okay, and now take the limit as x goes to the right, far to the right. But if you compute this one, x minus 1 over x, so they are equally power 1. Right? So you just need the coefficient. This is coefficient 1, this is coefficient 1. So this gives you 1. The same as the right hand side, x plus 1 over x. So this is 1. So this what's in the middle is squeezed between this 1 and 1. So at the end you have this limit. It's just 1. Okay. So this what tells you that when x is large, rounding x to the nearest integer, lower integer, divided by x is just 1. Equally about equally large, I would say. Okay. Questions? All right. In the end, we would say that the line y equals m is called the horizontal asymptote. of y equal f of x if the limit of f or to the left is L. Okay, so then one example is that um, 2/3 is the horizontal asymptote. Uh, why? Because if you take this limit, okay, and you divide top and bottom by, let's see, the largest power, 4. Okay, so you see that cube divided by power 4, this is linear. Power 1 divided by power 4, this by power 4, then that give you limit zeros. Okay, so the only thing left is just 4 divided by 6, 2/3. Okay, so y is 2/3. Sorry, this line y at 2/3 is the horizontal axis or on here. So this is the x-axis is horizontal asymptotes. Okay. All right, so let's take a break for 5 minutes.
Yes, sir.